All right, so I put a summary on the board of basically what we've done the last couple of classes, how we utilize the first and second derivatives in order to figure out what a graph looks like. We've been through this. This we've done like 2 days. This we did last class. So we can find where a function is going up and down by setting the derivative to 0, number line, test points, right? Y'all feel comfortable with this? Okay. And then anywhere where we see our function go up and then down, we will have a local maximum. Anywhere where we see the function go down and then up, we have a local minimum. All right, so this is actually going to be pretty important to us today for what we're going to do. And then we have the same sort of procedure, but with the second derivative. We set it to 0, we do a number line, we pick test points, and that'll tell us where our function is either concave up or concave down, right? Anywhere that your function switches from being concave up to concave down, we call that an inflection point. If it goes from concave down to concave up, we call that an inflection point. But this particular case, where it goes from concave up to concave down, in business, when you have like a profit function, I talked about this last time, this is called a point of diminishing return, right? So this is not a point of diminishing return, only this case, all right? We'll see this later. So I thought today what I would do was I would try and motivate all of this with a word problem to give us an idea of how we could use this like in a real world setting, all right? So last class the video didn't come out. I had a problem with my SD card, so I apologize, but this is on video, so you can go back and watch it and copy this down. I don't need you to write all that right now. So here's what I was thinking for this word problem. So here's an application. And I'm going to try and make it somewhat related to a business model or something that would involve money, and if you had a business, you might think about this. So let's say that I'm a farmer, all right? And I want to build this enclosure, and it's going to be 3 pens. So we're looking from the top down. These are pens. And I'm going to put animals in these pens, all right? Chickens, pigs, whatever, I don't care, right? So we have 3 identical pens that I'm going to build, all right? And what I need to do is I need to have a total area of 400 square feet. Okay, I need a total area of 400 square feet for these pens. That means all the pens together is 400 square feet. With me so far? Now there's a bunch of different ways I could do this, right? I mean, just to kind of get an idea. I could make it like this, where this side is 20 and this side is 20. And then the total area would be 400, wouldn't it? Okay. I could do it like this. I could do 10 and then make this side 40, right? And then have my pens there. That would work also. And I could pretty much come up with any other combination. I could do, a 5-foot pen. And then what would this have to be? What would this have to be? 80? Right? Like that? Understand? You get the idea here? You sure? Okay. So we haven't got to the question yet. I just want you to understand that when I'm building these pens, I have a bunch of different ways I can do this, yes? But here's the catch. When I build this fence, I actually want the animals to not be able to see each other because they'll start fighting or something like that, right? So these walls right here, these have to be solid walls, all right? Everything else can be chain link fence. With me? So I'll show you in green. This can be chain link, this side can be chain link, everything here. So whatever animal's in the middle, it's going to kind of suck, right? Because they can't see out the sides, they can only see out this way. These two, they got the corner lot, right? They can see all around except for this wall. Still good? So the green is chain. And let's say that these blue walls are going to be some sort of brick or something like that. Okay? Now that chain link fence is pretty cheap, right? I can go and buy that, it's pretty cheap, but having someone build a brick wall is going to cost me a little more money, right? So let's just make up some costs, all right? I'm just going to make these up, these are not real numbers, but let's just say to have the chain link fence built, I'm going to pay $15 per linear foot. All right? So I'm going to pay someone, they're going to come out here, and for every foot of fence that they put in, it's going to cost me $15. All right? And then let's say for the brickwork, it's going to be $25 per linear foot. Y'all still with me? Anybody have any idea what my question is going to be now?
How much will it cost to build a pen within the specifications?
Okay, so how much will it cost me to build this pen with an area of 400 square feet, right? How much will it cost me? But there's different ways I can build it, right? So that question is not quite what I want. The most efficient way to build it. What is the cheapest way I can build this fence? Right? What's the cheapest way? That's called an optimization problem. And think about what we've been doing. We've been taking functions and we've been trying to find out where the highest points and lowest points are, right? Maximums and minimums. What I need to come up with right now is a function that represents the cost of building this thing. And then I need to find its lowest point. That's what I need to do. That kind of makes sense? Okay, so you need to help me build a cost function now. How much will it cost me to build this fence? And here's the thing. I don't know what the dimensions are. Let me put the question up here. What should the dimensions be in order to minimize the cost? Unless I don't care about money. If I don't care about money, I just build it, right? Just build it however the hell I want to build it. But if I'm wanting to save some money, I want to do this as cheap as possible, but still give these animals the 400 total square feet, right? All right, so this is what calculus allows us to do. This is what that derivative allows us to do, is to find these lowest points on graphs, or highest points. So let's try and build up a cost function. How much is it going to cost me to build this? Well, I don't know what the dimensions of this pen are, right? I don't know what it is. I don't know how to build this yet. So what I need to do is start assigning some variables. So why don't we call this distance from here to here, why don't we call this distance x? All right? That fair? And then why don't we call the distance from here to here y? We good? Okay. Now, we need to come up with a cost function. So here's how we go about this solution. We need to first find our cost function. which I will call C of x. So can you tell me right now, well, you know what, let's call it just C right now. Okay, let's not call it C of x, because I don't know if that function is going to depend on x or not yet. Let's just call it C. Can you tell me what the cost of this, if I built it like this, how much it's going to cost me? So what would C be equal to? See if you can figure this out. How much will it cost me to build this piece of fence from here to here? How much is it per foot? It's the chain link fence, right? So that piece right there is going to cost me $15 for each foot. How many feet is this? X, we don't know, right? So do you all agree that this piece right here is 15 times X? Then I have to build that piece over there. That's another 15 times X. So far I have 15X plus 15X, right? What else? Keep talking chain link fence right now. 15Y. That's going to be this piece to this piece, right? That's 15Y. And I mean, not 15. 15Y, sorry. 15 times Y. And then another one on the backside, 15 times Y. So that goes there also, right? Yes? 15Y plus 15Y. All right. Am I done with my cost? No, I'm not. Now I need to take into account the brick part. And that's going to cost me this much, or this and this, right? So how much is that going to cost me? $25 times however long it is, which is X. And then another one, 25 times X. So I have out here 25X plus 25X. Y'all good? Does that cover everything there? We've got all the walls, everything's done. Okay, we have a lot of like terms here. We've got a bunch of X's and a bunch of Y's. Let's put everything together. My cost will be 15 and 15 is 30. That's 50 X's. So what, 80 X's? 80X plus 30 Y's. There we go. That's my cost, right? So if you provide for me the X and the Y now, I will be able to provide you the cost. Agreed? And I drew some pictures up there, the different ways we could do it. We could have done it like, 20 and 20. We could have done it like 10 and 40, right? All these different ways we could have done this. So if I plug in 20, 20, I'll have a certain cost. If I plug in 10 and 40, I'll have a different cost. But the cost will be different each way we do it. Do y'all understand that? My Cal 1 students always have a problem. They think it doesn't matter how we build it, we're going to have the same cost no matter what. But if you plug in 20 and 20 right here, if you did that on your calculator, 20 and 20, you would get a number. And if you plug in 10 and 40, you would get a different number. So it's a different cost depending on how I make these dimensions. Y'all okay with this so far? All right. What we need to do now, and this is the tricky part, is we need to somehow make it so that our cost depends on only X. Right now it depends on X and Y, right? You have to give me the X and the Y, right? I would like this to only have X's in it. And the reason I want it to only have X's in it is because then it will be a function of X. And if it's a function of X, like f of X, then we can do all the derivative stuff and everything else we've done. So I would like to try and eliminate Y, get the Y out of here. What is the one piece of information so far in the problem that I have not used that was given to me? What's the one thing I haven't used over here that was given to me in the original problem? The 400 square feet of fence, right? I can't just pick any X and any Y here, right? I'm not free to pick anything I want. There has to be a relationship between that X and Y. They have to multiply to be what? 400. Okay, so right now at this point, I'm going to try and squeeze this in here. We already know that's $15. So now I'm going to try to eliminate Y. All right? And I'm going to use the fact that x times y must be 400, right? I know that that's true because that's the area. According to my picture, if I take x and multiply times y, that needs to be 400 at the end of the day, doesn't it? So what I'm going to do with this now is I'm going to solve it for y. Okay, take this and solve it for y. How would you solve for y there? Divide both sides by x, right? Understand? So what I'm saying here is that y has to be 400 divided by x. So now I come back to this equation right here, and I replace y with 400 over x. Got it? So now at this point, I'm going to take my cost, which is 80x plus 30y, and I'm going to rewrite it as cost equals 80x plus 30 times 400 over x. So I just replaced that y with 400 over x. And then I'm going to do one more thing to that. I'm now going to write that as c of x equals 80x plus, what is that, 12,000 over x. What did I do there? I just multiplied 30 times 400. And notice I put c of x instead of c. That's because I'm stressing to you now that in order for me to determine the cost of this thing, all you have to give me is x. We have created a formula that if you just give me this side, that will spit out the cost of building this thing. It takes into account the chain link fence, the brick. It takes into account that the total area has to be 400. It's all incorporated in that one function. All right? So hopefully what I'm trying to show you is that, like real world, you have to turn it into mathematics. Then you do all the math that we've been doing. Let's try and figure out right now if we can determine where we have a local minimum on that function. Let's see if we can find a lowest point on that graph. How would we do that? How would I find the lowest point on that graph? What's that? I just had it on the board, right? You take the first derivative, right? You set it equal to 0. Number line, test points, and what we're looking for is down then up. If we can find a place where we go down then up, then we will have found a local minimum. Understand this? Okay. All right, now we need to take derivative of this. So before I take the derivative, let me rewrite it so that it looks a little nicer. Do you agree that if you were running a business, you would want to know this number? You would want to know what's going to minimize your cost, right? You would want this information unless you wanted your business to go into the ground, right? You just spend money and not even care about it. Imagine this on like a larger scale, right? Imagine you're building a skyscraper, right? I mean, you want somebody in there that can handle the mathematics behind finding optimum solutions to things. All right. I think you can all handle this derivative. I hope. What's the derivative of this? I'm taking the derivative of this function. What is it? 80. Okay, that part. Just 80 comes down. Derivative of x is 1. Okay, this part, y'all see why I brought the x up now, right? So I could use the power rule. So I bring that negative 1 out. I get negative 1,200, or negative 12,000. X to the negative 2, right? X to the negative 2. That's my derivative, right? Okay, I need to set it equal to 0. So I take my derivative. I want to set it equal to 0, which means I'm going to set 80 minus 12,000 x to the negative 2 equal to 0. And you look at that, and you should probably be a little confused because this is the first time we've seen anything like this. All right, but let's not panic. Let's not panic. Let's just kind of rewrite it for a second, just to see if it helps us if we rewrite it. Okay. So if I rewrite that equation, it's 80 minus 12,000 divided by what? X squared, right? That's another way I could have written that. That's the same thing. Just drop that x to -2 down. And now watch this. If this is 80 minus this term, can't I move that whole term to the other side of the equation and it would become a plus over there? Just, if it's negative here, move it to the other side, it becomes plus. Y'all all right with that? So we've got this. We're almost there. Now, x is in the denominator of this equation, and I don't like it down there. I want to bring the x out of the denominator. So what I'm going to do now is clear the fractions. I'm going to multiply both sides of the equation by x squared. All right? That seemed like a legitimate move. Multiply here by x squared. Multiply here by x squared. These x's cancel. Those x squareds cancel. And now I have 80x squared equals 12,000. And I'm going to need my calculator to take a square root here in a second. I'm going to divide both sides by 80 now, right? So you're going to take 12,000, divide it by 80. It's 150. Y'all know what I did there? Yes? And then I'm going to take the square root on both sides. So I take the square root of 150. And I get, remember, when you take the square root, don't forget, when you take the square root, you have to do plus or minus. We're actually going to get two solutions here. X is equal to, are y'all comfortable with that idea? That you have to get a plus or minus when you take a square root? Yes? I'm just going to round that 3 decimal places. I get x must be positive or negative 12.247. Okay? Was that so bad to work on that? Does that seem all right? Now what? Number line. Okay, so now we're going to go to a number line. Let me keep my derivative there because I'm going to need it. There's my derivative. So I'm going to go to a number line. And I have negative 12.247. And I have positive 12.247. And that breaks my number line up into 3 regions, right? Now what? Test points, right? Now think about this for a second, though. All right, I really want you to think about this. X is the length of the side of the fence, right? X is this length. Does it make any sense for us to be talking about x's over here? No, it's negative. I'm not going to build a fence with negative length. It doesn't make any sense. So I'm actually going to throw this region completely out because it doesn't fit into the word problem, right? It doesn't fit into the word problem. But I should pick something over here. I should pick something over here. And, you know, I could pick any number in between negative 12 and 12, somewhere in there. I'm going to pick 1 because it's a nice little positive number. I'm going to pick 1. Is that all right with you? I'm going to pick 1. And then over here I need to pick another number. What should I pick? 13 is fine. And where are these numbers getting plugged into? The derivative. Okay, so I'm going to plug 1 into the derivative. So I'm going to go into the derivative, I'm going to plug 1, and then into the derivative, I'm going to plug 13. And when I plug 1 into here, remember that this is really over x squared, right? That's what that really is. That negative, x is negative 2. So if I plug 1 in here, I'm going to have 80 minus 12,000 over 1 squared. And 1 squared is, well, 1, right? So this will just be 80 minus 12,000. All I care about, though, is whether or not it's positive or negative. and this turns out to be negative. Does that make sense? Okay, so this is a negative number. I'm just going to put negative, circle it. That's negative. What does that tell me about my original graph of my original cost function over here in this region? It's going down. And this is starting to look good for us, isn't it? The original cost function is going down here. All I need now is to show that this side goes up. And if I show that, then I've shown that I have a local minimum here. Okay, so if I plug in 13, this is going to be a little bit more work. We have to do 12,000 over 13 squared, so we square that on our calculator. Yeah, so when I do this divided by this, okay, when I square it and do that, I get 80 minus 71.005, something like that. That's what I get when I do this calculation. And 80 minus 71, that's a positive number. So this is positive. And that's what I needed. I needed it to go down and up. That means this is a local minimum, right? Yes, of my cost function. So I think I'm ready to wrap things up here. Therefore, the cost has a minimum at x equals 12.247. Okay? Have we answered the question? Go back, if you wrote the question down, what was the question originally asking?
What should the dimension be in order to
Yep. What are the dimensions of the pen? This answer is only telling you what x should be, right? The dimensions means you need to tell me what x and y are, right? So we still need to get what y is. So go back and look in your work. Did we ever in our work have y equals something somewhere?
Yeah.
Yes, we did. What was it? It was y equals 400 over x, right? Remember that? That was in the equation we solved for y way back when. So if I take this now and I use this x, 400 over 12.247, then you get that y needs to be 32.661. And now I have the dimensions of the pen. The dimensions should be 12.247, and this dimension up here should be 32.661. Now, can somebody summarize, like tell me in words, what this means? Like, if we build it this way, what? It'll be the cheapest way to build it, right? And we will still maintain an area of 400 square feet. If we don't believe that, take this number and multiply that times that number. If you multiply these together, you're going to be close to 400. We round it a little bit, so it'll be close, right? Now, I'm going to add one more additional question. What is the cost? What is the minimum cost? So let me add that as the last part of this question. I asked you to find the dimensions that would give you the minimum cost. What is the minimum cost? So how would you find the minimum cost? Yeah, you can go back to your cost function right here, right? And you could plug into this just the 12.247. So if I do that, the cost at 12.247, it'll be 80 times 12.247 plus 12,000 over 12.247. And let's go ahead and do that on our calculators. Let's see what we get. Well, I'm going to let you do that. I'm going to let you on your calculator figure out what the cost is while I'm going to turn on the projector. I want to show you all something here. Excuse me, I'm just going to reach over you real quick. Yeah. Anybody have it yet? We got to see if this screen even comes on. It hasn't been working. Oh, yes. Okay, so what'd you get?
1,959.
1,900? 959 and 56 cents, roughly. I mean, there's probably some rounding in there. Everybody else get that? Everyone else got that number? Okay, what this means is that let's kind of flip this question a little bit. Farmer approaches my company, says, I would like you to build me this enclosure. It needs to look like this. It needs to be 400 square feet total, right? Will you build it for me? And you're bidding on it. You're trying to figure out, you're trying to outbid these other companies, right? Trying to compete. If you use calculus, you can actually figure out the cheapest way to do it, right? And so you might be able to bid a number, like maybe you bid this project at 3,000. So you're looking at, you're gonna have 1,000 for your labor and profit or whatever. Some other company comes in and they're just like, we're just gonna build a 20 by 20 pen, right? If they build a 20 by 20 pen, how much is it gonna cost them? If they do 20 by 20. Let's try it. If X is 20, what would you get? What can you guarantee me? It's gonna be more than this, right? Okay, so 12,000 divided by 20. $2,200. Okay, if you build it 20 by 20, it'll cost a little over $200 more in materials to, well, I don't know if we're including labor or not, who cares, right? But it's more expensive. So the company who's not using the calculus is either going to have a higher bid, or they may bid 3,000 also, but they're gonna have less profit because they've used up money on material they didn't need, right? Okay, so I'm going to do one last thing here. That's why I brought the projector up. I'm actually going to ask the computer to graph the cost function for us because we'll be able to see that local minimum. All right? And see, you don't even really have to do calculus. Like if you're like in a real business situation, you could actually, like let's say you didn't know any of this calculus, right? But you were able to come up with the cost function. If you're able to do that 80x thing, 80x plus 12,000 divided by x, right? That was it. Oh man. Darn it. I need to see if I can adjust this window. Hold on. Oh, here we go. So let's let my x-axis only go between, let's go negative 20 to 20. Let's go to 30. And let's let this go from negative 10 to 3,000. There we go. Better. All right, so I don't know how well you can see that. Can y'all see that okay? This is the graph of the cost function. So that person that comes in and builds that pen using x is 20 is going to cost them about $2,200, right? But because you ran a little bit of calculus, you're able to determine the 12.247, about right here, you were able to find that lowest point. Wait, this is counting 11, 12, so here's 12, 12.2. There it was. See, that's the lowest point on that graph. So what I was saying is if let's say you didn't know any calculus, but you could come up with your cost function, you could actually just come to a graphing utility like this, and you could say, well guys, what do you think, Bob? About 12? Yeah, we'll make it about 12. You know, and that would be better. It doesn't have to be 12.247. I mean, that would be perfect, but you're not going to be able to be that precise anyway, right? So you go, oh, we'll make it about 12 foot, right? Understand? You just don't want to make it like, oh, we'll do a 25 foot, because you're spending more money, right? Does this make you feel like we're doing something related to business now? Okay, all right, because that's what this is all about, right? The calculus is just the tool that we use. The hard part about the business is how do you turn the problem that you're dealing with into the mathematics. All right. We are going to spend more time on that next week, and maybe we'll do another one of those today. But I wanted to let you do a problem today on your own, just to make sure everyone's kind of on the same page before we get too far into these optimization problems. I want to make sure everyone's comfortable with those steps that I put up at the beginning of class. So this is going to be kind of a group work. I'm not going to collect it, but I do want everyone working. And what I'm actually going to give you is one of your homework problems. I did catch up on the videos. Okay, so I'm caught up through 12.2. But on 12.2, I did not do 3 of the problems because I intended on doing them in class. So what I'm looking at here, this is from 12.2. This is page 662. And I'm looking at number 51. And the problem is f of x equals x plus 1 times x squared minus x plus 2. That is the function that you're given. And here's what I want to know, all right? Here's what I would like for you to do right now. First thing, find where f is increasing and where f is decreasing. The second thing, find any local extrema. That means find any local maximums or minimums. The next thing, find where f is concave up and where f is concave down. And then 4, find any inflection points. So you're basically going to be working with the first and second derivative, setting them to 0, test point, number line test points. That's what you're going to do, right? Yes? There's a problem though, and this is what I'm curious to see how you're going to handle it. This function right here, you have to take the derivative of it. So I want you to raise your hand after you get the derivative, because I need to make sure you do it right. This is not a clean derivative like the ones we've been doing. You got to do a little more work here for this one. So let's see how you do with it. If you have a question on it, talk with your table. And if y'all can't figure it out, if the whole table is stumped on how to take the derivative of that, then raise your hand. I'll come by and help you out. All right? Okay, get to work. Let's see how this goes.